Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, I'm back after a week's vacation and I'm raring to go. I had a lot of fun last week bicycling along the lakes in northern Michigan, Lake Huron, and to a greater extent, Lake Michigan. Let me pull out my portable map of my home state of Michigan. So I was up here basically bicycling from the east side of northern Michigan to the west side, finishing up in Traverse City. There were a lot of highlights. It's a real beautiful part of the country. One of my favorite parts was riding through what's called the Tunnel of Trees, which is a 20-mile section or so of road that goes right along Lake Michigan between Mackinac City and Petoskey. And it's a windy road with lots of hills. You're right there up on the bluffs. Lake Michigan is off to the right, but way down a couple hundred feet, or at least it seems like it's about a couple hundred feet. And it's just a lot of fun riding. Other highlights would be probably from Petoskey to Charlevoix, where you're closer to the lake in terms of your elevation. You're right there along the lake and you're riding on bike paths, and you can stop, at the beaches when you get an opportunity. There's lots of great resort towns to bicycle through. And of course, it wouldn't be a Chuck Ridgway vacation if there weren't lots of good food to eat. After bicycling an average of 50 miles a day, you get pretty hungry. And this actually was the first bicycle trip I've had in a couple years where I didn't actually gain weight on the vacation. So that gives you an idea of how hungry you can be after some of these rides. Well, enough about my vacation. Before we dive into today's topic, I want to thank Don Clutterbuck, who stepped in last week and gave us an update on Cscape 10.2, as well as what's going on and what's new with OCS 360. So thank you, Don. If you haven't checked out last week's topic, then I would suggest you go to our YouTube channel and do that as soon as possible. Okay, so let's talk about today's topic. All summer long, this is the CPU summer, we have been covering Horner's new modular controllers, spending a lot of time on the CPU250, which we will today again. However, we have another new CPU model coming later this month, the CPU300, which we'll start covering here in a week or two. Okay, but for today, here's our topic. CPU250 I/O configuration using variables. Well, the ability to make some I/O configuration adjustments from variables instead of necessarily having to do a programming change in Cscape when you want to make an adjustment on a machine on the fly is a capability we've been adding to our products for some time now. The Micro OCS has this capability to a certain extent, as does OCS I/O, and certainly the CPU250 does as well. So when is this useful? Well, we're going to talk about that today. And without further delay, let's dive right in. Okay, we're going to start with a quick review of the CPU250 like we always do, but we'll keep that nice and short, and then we'll dive right into our topic. Why would we use variables for configuration? That's the first question we're going to answer, and then we're going to talk about some of the I/O adjustments that you can make at runtime. You can't make all of the adjustments, but you can adjust quite a bit of the I/O, and there'll be plenty of demonstrations. All right, here we go. All right, the new micro modular controllers are the CPU200 and the CPU250. They're part of our micro series, which is our entry-level product line for simple and smart applications. There's a whole lot of applications you can solve with the micro series that now includes the CPU200, which is on the right at the bottom with no built-in I/O. You add I/O strictly on the side using OCS I/O modules. And then in the upper right, we have our CPU250, which does feature built-in I/O, but you can also add additional I/O using OCS I/O modules. All right, we've been focusing a lot on the CPU250 these days for good reason. It's got tons of great connectivity with Ethernet and serial ports and CAN ports, supports all those great protocols that you see in the lower left there, has all kinds of other capabilities, including, as I've already mentioned, the ability to add OCS I/O modules on the side directly to add additional I/O. But the star of the show is the built-in I/O for the CPU250. It's got a total of 34 built-in I/O points, 8 of which are what we call flexible inputs. They can be digital or analog. And we also feature 8 analog outs, which is a large number of analog outputs for a product in this product category. And today, we're focusing, as I've mentioned already, how you can do some I/O configuration with variables so you can make some runtime adjustments of your I/O configuration without having to pull out Cscape. All right, now let's talk about configuration. Typically with PLCs and other control type devices like a Horner OCS or a Horner Modular Controller, how does that typically work? Well, traditionally, you would use your application development software program and you would configure your I/O as you develop your machine. And after you deploy your machine, you wouldn't make any configuration changes at all. And typically that works just fine. But there are some scenarios where making some adjustments without having to drag your application programming software out to the factory floor would be useful. Let's talk about that now. Let's start with Ethernet type changes. This is a very common thing that can change after a machine has been deployed. So let's say that the IT department does a kind of reformatting or upgrade of the factory network and your machine is sitting on your customer's factory network. Well, they'd like to be able to modify the IP address, netmask, those sorts of Ethernet type parameters without making a configuration change, So you could, and we have for quite some time now, given customers the capability of assigning variables to the Ethernet parameters. IP address, netmask, default gateway, those sorts of things. So as changes are made over time, in your original program, you could utilize those variables, create some custom screens, that sort of thing, or maybe a custom screen on a SCADA package or an HMI that would allow those IP address and those sort of Ethernet parameters to be changed. So that's a very common thing that we've supported for some time. But there's another scenario that also can occur, and that is maybe at some point after you've deployed your machine, your customer needs to swap out a sensor. A sensor has failed, it needs to be swapped out. And maybe the original sensor was 4 to 20 milliamps, and the new sensor, they can't find one of those in stock. There is the same sensor, but with a 0 to 10 volt output on it instead. So it would be nice to be able to support that sensor without having to reprogram the controller. So could that be done? Well, in the case of the CPU250, absolutely, because we've given you the capability of modifying some of your parameters, such as sensor ranges, on the fly. And how would you do that? Well, let's take a look. All right, so what I have on the screen here is a table that shows what changes can be made through variables to flexible inputs. Now, there are 8 flexible inputs on the CPU250, inputs 9 through 16, and each flexible input has 4 configuration words that allow you to adjust its functionality. Okay, so that table on the right there shows 4 words, and that's 4 words for each of the 8 channels. And the types of things you can adjust are, first of all, is that input used for digital purposes or as an analog input? If it's selected as a digital input, what is the voltage range? 24, 12, 5, or custom? If it's custom, what is the on threshold between 5 and 20 volts? What is the off threshold between 5 and 20 volts? So if you're using a flexible input as digital, that's what you can adjust based on that third column in the chart on the right. Now, what if you're using a flexible input for analog purposes? Well, you can select the range. Is it 0 to 10 volts, 0 to 20 milliamps, or 4 to 20 milliamps? And then once you've selected the signal type, how do you want the data to be scaled? Okay. Do you want to take advantage of all the bits in the analog input word and just have 0 to 32,000 from min to max? Or would you like something maybe mathematically simpler, like 0 to 1,000 for the scaling, where 0 is minimum and 1,000 is maximum? That gives you a nice, simple 0.1% resolution, and in some cases can make scaling math very easy. So that all comes down to your preference, but that could be changed on the fly as well. Now, of course, the most common thing that would be changed on the fly would be the signal type of the sensor, whether it be analog or digital, okay, because maybe that's what you can find. Now, as I've mentioned, we have 4 words for each flexible input for configuring these things we've talked about so far. For all the channels that are used as analog, there's a separate configuration word, just 1 word total for all the channels that are analog for adjusting the filtering. So 0 at minimum filtering, 7 at maximum filtering, and it can be in between to balance responsiveness versus signal stability. And then for all channels that are being used as digital, you've got a single word to configure between positive logic and negative logic. Now, 95% of the time, or maybe even more than that, you're going to be using positive logic. But if you do use negative logic, it's available, but you don't have the option of the custom thresholds anymore. Okay, so that's what you can do on the flexible input side. Now, just one more mention on how you would deploy this. So for each of your 8 channels, if you're using register-based programming, you would assign 4 consecutive R-type registers to hold this information, this configuration information. If you're talking about variable-based programming, which we've been encouraging for some time, then you're talking about an array-type variable of the word type with a dimension of 4. One of those variables for each of the 8 channels. So that's how you would deploy that. And you would just need one simple variable for analog filtering and another simple variable for the digital input mode. All right, now what about the analog output side? Is there anything configurable here as well? Well, there is, okay? You can configure signal type, data range, and what's called halt state. What happens to the analog output signal when the controller goes into stop mode? Does it continue sending out the value that was there before the controller went into stop mode? That's called hold value. Does it go to minimum, which is usually 0 volts or 4 milliamps or 0 milliamps, etc. So you can adjust that as well. Now, I'll be honest, this isn't quite as useful as making changes on the analog input side. Why is that? Well, because the analog outputs are already segregated by signal type. So the first 4 analog outputs are milliamp type, and the next 4 analog outputs are voltage type. So really, if you're going to be using a voltage sensor instead of a milliamp sensor, you'd have to actually change channel locations where you actually wired the sensor. So this isn't quite as useful in terms of changing on the fly as on the input side, but the capability is there as well. And you can see you've got 3 words of configuration per analog output. All right, and so that means 3 consecutive registers per analog output if you're using register programming, or 1 word type array with a dimension of 3 for each analog output channel if you're talking about analog output configuration. Now, one thing to keep in mind, maybe you just want to make the analog input configuration assigned to variables, and maybe you want to fix your analog output configuration. That's something you could do as well. So you have flexibility there. All right, so now let's show you through demonstration how we can accomplish some of this I/O configuration using variables. Okay, let's take a look at our demo. All right, I'm in Cscape 10.2. Now, you only really need to have, I believe, 10.1 Service Pack 1, but 10.2 is being posted this week, if it's not there already. So I thought I would use that today. And let's go ahead and take a look at our demo. All right, now before I dive into the Cscape side of things, let's take a look at what I've got going on the bench for a demonstration. So you'll notice there's my CPU250, but you'll also notice I've got another Horner product here. What's that all about? Well, the CPU250 doesn't have a built-in screen. So if you're going to manipulate the hardware configuration of the CPU configuration from registers or variables, then you're going to need some way of doing that. And one of the ways you could do that is with a remote screen, whether it's an HMI screen or whether it's a SCADA screen from a control room or something like that. And remember, we're not going to be making I/O configuration changes very frequently, so it doesn't necessarily have to be something that you access all the time. But to simulate that remote screen or remote SCADA screen, I have used a Micro X7, and I'm just using it as an HMI right now. And I have it talking to the CPU250 over Modbus TCP using what we call native addressing, so that the micro and the CPU can talk to each other using Horner nomenclature. You don't have to do any conversion to Modbus register types or anything like that. But anyway, the whole purpose of this demonstration is to show you how I can manipulate the I/O configuration from a remote screen without pulling out Cscape. All right. So that's what I have going on the bench. Let's take a quick look at Cscape now to see what programming is required. All right, and we're starting in this program that's residing in the CPU250. And let's start in the hardware configuration, which makes sense. Okay, now we'll go to the local I/O tab. All right, now there is no configuration on the fly for digital inputs, nor for digital outputs, so we aren't doing anything there. But on the flexible input side, as we showed on the slides, we do have the ability to assign variables here. And for each input channel, for each flexible input channel, we can assign a variable that is a word type variable, an array word type variable with the dimension of 4. And again, we have one of those array variables for each of the 8 flexible input channels. Now, in addition to that, we've got a single word variable for the filter for the analog channels and a single word variable for the positive or negative logic selection for all the digital channels. Okay, so those are the variables we've assigned for flexible inputs. Now, on the analog output side, we also have the ability to assign word array type variables, this time with a dimension of 3, for the 8 different analog channels that we have here. Okay, so that's really all that's required there. All right, now, where are these variables being manipulated? Well, they're actually being manipulated by the remote screen that I showed you on my bench over Modbus TCP. So we obviously have to set up Modbus TCP. In this case, we're just using the CPU250 as a server. Okay, so we've just checked that checkbox and made sure we have IP address, netmask, and gateway configured. Now, in a real application, I would assign variables to these as well, but I've just hard-coded it here for demonstration purposes. All right. And then there's one final step, and that is this. Because the data to manipulate those variables or to fill those variables is coming in over the network, I had to do some variable mapping or some register mapping to those configuration variables. So here are those configuration variables. Okay, here are the word arrays for the flexible inputs. Here are the word arrays for the analog outputs. And then here are the simple variables for the filtering and for the positive or negative selection. And for each one of these, I have assigned a starting register for these. Why did I have to do that? Well, because the data is coming in over a network. They have to be at a known memory location. So effectively what I have done for all this configuration data as an aggregate, I have, I believe, 58 registers assigned here, starting at register 1001 and going through 1058, because remember 56 and there's 2 additional ones after that, 57, 58. So that's what I've got going here. So there's no other programming required in the CPU250. All the manipulation is being done elsewhere. All right, now let's take a quick look at the program that I have running in the micro. Okay, so here, if we take a look, we can see that in the hardware configuration, we have configured a, oops, I'm actually looking in the wrong program again, aren't I? There we go. Let's go back to the right spot here. All right, that's the CPU250. Let's go to the hardware configuration for the Micro X7. There we go. Hardware configuration. And now let's look at LAN 1. This time we're not a server. This time we're a client. So the Micro X7 is the Modbus TCP client, and it's scanning those registers that I talked about where the configuration data is mapped. It also happens to be scanning the standard I/O data as well, although that's not a requirement. That's just what I added to my Modbus map here. But again, you don't have to do this Modbus part to make this work. You just have to have some way of manipulating those variables in the, you have to have some way of manipulating those variables in the CPU250 that's controlling the I/O configuration. Okay, and then I have a little bit of logic here for controlling things like visibility on the 2 screens that I've created. So this is a screen that contains all the flexible input data, okay, and I have the ability to manipulate that with simple toggle switches for digital and analog, some text tables for selecting through the different available ranges for digital and analog types, And then, of course, I also have text tables for the different available data ranges as well. So, and all these will either be displayed or not displayed, depending on whether the channel is configured for digital or analog, depending on the voltage threshold if it's digital, or depending on the signal type if it's analog, all those sorts of things. All right, so enough of this on Cscape. Let's take a look at what it looks like on the bench and show you what's happening in action. Okay, so for this configuration, what I have is for the first 4 analog channels, I have set those for analog. This is a toggle switch that toggles between analog and digital. The first 4 flexible channels I have set for analog. The first 2, I've got a type of 4 to 20 milliamps, and the next 2, I have a type of 0 to 10 volts. And because I could, and for demonstration purposes, I also set the data range or the scaling differently for the current channels as I did for the voltage channels, although you certainly don't have to do it that way. Then the final 4 flexible inputs I have set for digital. Okay, the first 3 being 24 volts, and the last one being set for a custom data range. Okay, not data range, a custom on and off threshold. And right now it's set for an on at 20 volts and an off at 10 volts. And then over here, I have a variable power supply. So right now, if we take a look at I16, which is the one we're talking about here, which is the last of the flexible inputs, that LED is off. Okay, so until we get to 20 volts, that LED is going to stay off. Once I get up to 20, then you'll see it turn on. There we go, it turned on. And then once we get back down to 10, you'll see it turn off again. Okay, got to go down further, down to 10, and you can see it is off. Okay, we're down around 7 volts now. All right, now let's adjust that range, and let's say that we want to adjust the threshold for on to be 18 volts instead of 20. So now, if we bump up as soon as we get to 18, we should see it turn on, and we did. And then again, we have to get down below 10 before it turns off again. There we go. All right, so as you can see, we can very easily manipulate any of these parameters that are accessible through those configuration variables that we assigned. And then if we move over to the analog output side, you can see we've got similar things happening here as well. So we've set the first 4 channels for 4 to 20 milliamps, the next 4 at 0 to 10 volts. We've manipulated our scaling a bit, or our data range there, and we've set our stop value to be minimum for all the analog channels. But we could change these on the fly if we had a need to. Again, as I mentioned earlier, having the ability to change analog input settings is a little bit more valuable than analog output settings, frankly, because you run into that scenario much more frequently. Okay, so that's our demonstration on the bench. Okay, that does it for our topic for today. Don't forget to sign up for training. We are getting pretty full with our October course. So if you're interested in basic training in October at Horner, at the factory, at the training center, I would suggest that you act now. Okay, still plenty of trade shows left. Don and crew were in Grand Rapids, Michigan, while I was cycling around just north of there. But we've got things going on in Houston, Odessa, Texas, Lake Buena Vista, Florida, as well as WEFTech in Chicago. So still plenty of opportunity to check us out at one of these trade shows. All right, don't forget, you can interact with Horner on our website, on our YouTube channel, or on LinkedIn. And our YouTube channel is where you'll find last week's presentation that Don gave on Cscape 10.2, as well as what's new with OCS 360. All right, next week, we're going to be talking about the new CPUs and OCS-I.O. in regards to CAN wiring. You know, how do you wire those guys up? We've had several questions from folks on different scenarios, and we're going to cover those next week. If you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything. And if you choose notifications when you subscribe, that's that little bell, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, let's all get out there and do some good.